In this video, I would like to introduce the idea of an inverse trigonometric function. We know that functions like the square root of x and x squared are inverses of each other. Exponential and logarithmic functions are also inverses of each other. So what does the inverse of a trig function like sine or cosine look like? Well, remember that when we're looking at a trigonometric function, the input value is an angle, sometimes in radians, sometimes in degrees. The output value is a ratio. It is a real number between -1 and +1. Here's a graph of the sine function. And we need to remember that the inverse function switches these input and output values. I'm going to write the inverse function for sine like this: y equals sine inverse of x. That is not the same as y equals 1 over sine of x. This -1 superscript here is not a power of -1. It designates an inverse function. And our input and output values for this inverse function are reversed. So the input of this function, the x value, is now a number or a ratio between -1 and +1. The output value is now an angle. So some x and y values on this inverse function can be found just by reversing the values from the graph, the table of values above. We have 0, 0, 1, pi over 2, -1, negative pi over 2, and so on. Now, if I continue just with the points from the table of values above, I would also see 0 pi and 0 negative pi. But there's a problem here, because this does not appear to be a function. I have an input of 0 in several different places, and it's leading to 3 different output values. Well, like many other functions, we must restrict the domain of sine of x so that its inverse is actually a function. We need to make sine of x 1 to 1, or consider an interval of the graph where it is 1 to 1. The typical way that we do that for sine of x is to consider the interval from -pi over 2 to +pi over 2 on the graph. We will only look at this segment of the graph. Therefore, we won't have to worry about any values outside of that segment. We can forget about these 2 points. And when we reverse that picture, we get something that looks like this. The graph of sine inverse of x appears something like this. It now has x values of real numbers, -1 and +1 are the minimum and maximum, and the y values are now angles in radian measure, pi over 2 and negative pi over 2. This is the graph of y equals sine inverse of x. I want you to notice the domain and the range of this graph. Because we restricted the domain of the sine function from -pi over 2 to +pi over 2, the range of sine inverse is now -pi over 2 to +pi over 2. The domain of sine inverse is now -1 to +1. In a similar way, we can restrict the domain of the cosine function and the tangent function and create inverse functions for those as well. For cosine of x, we typically restrict the domain from 0 to pi. We consider this interval of the cosine graph, and these are the x and y values that we will reverse to find cosine inverse of x. It will contain the points 1, 0, 0 pi over 2, -1 pi, to name a few. The graph of the inverse cosine function looks something like this. Its maximum is at pi on the y-axis, and it has a domain of -1 to +1. So cosine inverse of x has a domain of -1 to +1 and a range from 0 to pi. Finally, look at the graph of y equals tangent of x. This graph is also periodic. The picture repeats itself every pi units. And we're going to consider just one period of this graph to find its inverse. Let's look at the region from -pi/2 to +pi/2. Y equals tan inverse of x has a domain of -∞ to +∞ and a range of -pi/2 to +pi/2. The graph looks something like this, with horizontal asymptotes at -pi/2 and +pi/2. It's important here again to note the range of this inverse tangent function. In the next video, we will begin to evaluate inverse trigonometric functions, and it will become important to keep in mind the range of each of these inverse functions.